Welcome. Need some gentle help with getting to sleep? You are in the right place and have made an excellent decision to listen to a compilation of facts combined to tell a bedtime story for sleepy adults. Dark matter studies? Einstein wrong. Get clued in and sleep on it? Let's begin. Part 1. The serene mystery of the cosmic night. Close your eyes for a moment and picture the night sky. Stars scattered like grains of sand. Galaxies spinning slowly in the dark. And between them, nothing but space. Or so it seems. We're going to explore something wonderful and strange. Something that fills most of the universe, yet we cannot see it. We call it dark matter and dark energy. These names sound mysterious, and they are. But they're also deeply calming to think about, because they remind us that the universe still has secrets, that there are gentle puzzles waiting in the dark, and that we, small as we are, can still wonder about them. You don't need to understand everything now. You don't need to remember every detail. Just let the ideas wash over you like waves. Let them carry you softly toward sleep. The universe is vast. It has been here for nearly 14 billion years. It will be here long after we're gone. And in all that time, in all that space, most of what exists is invisible to us. Not because it's hiding, but because it simply doesn't shine. Dark matter doesn't give off light. It doesn't absorb light. It passes through telescopes as if they weren't even there. And yet we know it's real. We can feel its presence in the way galaxies move, in the way light bends around clusters of stars. Dark energy is even stranger. It's a kind of pressure that fills all of space. A whisper that pushes everything apart. It makes the universe grow faster and faster, like a slow breath that never ends. Together, dark matter and dark energy make up about 95% of everything. All the stars, all the planets, all the light we can see, that's just 5%. A tiny sliver of the whole. And that's okay. It's more than okay. It's beautiful. Because it means the universe is bigger than we imagined, stranger than we thought, and full of mysteries that invite us to look closer, think deeper, and rest easier knowing we are part of something so much larger than ourselves. Now we'll walk through this mystery together, slowly, gently, one step at a time. We'll talk about how scientists first noticed something was wrong. How galaxies spun too fast to hold together. How clusters of galaxies moved as if held by invisible hands. We'll talk about the ideas people have had. The particles that might make up dark matter. The theories that suggest gravity itself might work differently to how we thought. We'll talk about recent discoveries. New measurements that have made scientists pause and reconsider. Not because the old ideas were wrong, but because the universe is showing us something subtle, something new. And we'll talk about dark energy, the force that stretches space itself. The reason the universe will keep expanding forever, growing quieter and colder, until the stars themselves fade away. But don't worry, that won't happen for trillions of years. At night the stars are still shining, the galaxies are still spinning, and you are here, safe and warm, thinking about the dark. There's something soothing about cosmology, about thinking on the largest scales. It puts our worries in perspective. It reminds us that we are part of a story much older and much grander than our daily lives. So settle in. Let your breathing slow. Let your body relax. And let's begin our journey into the dark. Part 2. The stars that spun too fast. Our story begins in the middle of the 20th century. Astronomers were studying galaxies. Those vast islands of stars, each one containing hundreds of billions of suns. They wanted to know how galaxies moved, how fast they spun, whether the stars at the edges moved differently to the stars at the center. To understand this, imagine a merry-go-round. The horses near the center move slowly. The horses near the edge move faster, sweeping through space in wide circles. That's because they have farther to go to complete one rotation in the same amount of time. Galaxies, scientists thought, should work differently. In a galaxy, most of the mass is concentrated at the center. Millions of stars packed close together. The outer regions are sparser, fewer stars, more empty space. So the expectation was simple. Stars near the center of a galaxy should move quickly, pulled by all that mass. Stars far from the center should move more slowly, like planets in our solar system. The farther out you go, the weaker the pull of gravity, the slower the orbit. But that's not what astronomers found. In the 1960s and 70s, a scientist named Vera Rubin began measuring the speeds of stars in spiral galaxies. She used telescopes to watch how light from those stars shifted, redder or bluer depending on whether the star was moving away or toward us. This technique is called measuring rotation curves. And what the late Vera Rubin discovered was startling. The stars at the edges of galaxies were moving just as fast as the stars near the center. Sometimes even faster. They weren't slowing down at all. At first this seemed impossible. If you calculate the gravity from all the visible stars, the outer stars should fly off into space. There shouldn't be enough mass to hold them in their orbits. But the galaxies weren't falling apart. They were spinning smoothly, held together by something invisible. Vera Rubin's work was meticulous. She measured galaxy after galaxy. And every time the result was the same. The stars moved too fast. The visible matter wasn't enough. Other scientists began to notice similar problems. Fritz Zwicky, decades earlier, had studied clusters of galaxies. These are groups of hundreds or thousands of galaxies, all bound together by gravity. Zwicky measured how fast the galaxies were moving within the cluster. And again they were moving too fast. If you added up all the stars, all the gas, all the visible matter, there wasn't nearly enough mass to keep the cluster from flying apart. Zwicky called this missing mass dark matter. He didn't know what it was, but he knew it had to be there. For a long time, astronomers hoped they'd find the missing matter. Maybe it was hiding in planets, or dead stars, or clouds of cold gas that didn't shine. But the more they looked, the more they realized there simply wasn't enough ordinary matter. Not even close. Whatever was holding galaxies together, it wasn't made of stars or gas or planets. It was something else. Something that didn't interact with light at all. And so the mystery deepened. By the 1980s, the evidence was overwhelming. Galaxy rotation curves, cluster dynamics, computer simulations of how galaxies formed. Everything pointed to the same conclusion. Most of the matter in the universe is dark, invisible, present only in the way it pulls on things we can see. Imagine standing in a dark room. You can't see the walls, but you can hear your voice echo. You know the room is there because of how the sound behaves. That's what astronomers were doing, listening to the echoes of gravity, watching how light and matter moved. and deducing the shape of something they couldn't see. It's a bit like detective work, piecing together clues, building a picture from shadows and whispers. And the picture that emerged was strange, beautiful in its way, but strange. The universe, it seemed, was mostly made of something we'd never touched, never seen, never even imagined until the evidence forced us to. Vera Rubin spent much of her career studying this mystery. She was patient, careful. She knew that extraordinary claims required extraordinary evidence. And she gathered that evidence, night after night, image after image. Her work helped convince the scientific community that dark matter was real, that it wasn't just an error or a misunderstanding, that the universe truly was full of invisible mass. And that realization changed everything. It meant our understanding of the cosmos was incomplete. It meant there were entire categories of matter we knew nothing about. It meant the universe was stranger, richer, more mysterious than we'd ever imagined. But it also meant something comforting. It meant the universe made sense. The galaxies weren't defying the laws of physics. They were following those laws perfectly. We just hadn't understood all the pieces yet. So take a breath. Let that thought settle. The universe is full of things we don't yet understand. And that's okay. That's wonderful even, because it means there's always more to discover. Always another question to ask. Always another mystery waiting in the dark. And now, as you drift toward sleep, you can rest easy knowing that somewhere scientists are still watching the stars, still measuring their motion, still piecing together the puzzle, one rotation curve at a time. Part 3. What we mean when we say dark matter. Let's slow down for a moment, take a deep breath, and ask a simple question. What is dark matter? We've talked about what it does, how it holds galaxies together, how it makes stars spin faster than they should. But what is it really? The honest answer is, we don't know yet. Not for certain, but we have ideas. Good ideas, based on careful observation and mathematical reasoning. And now we can explore those ideas together, gently, without hurry. When scientists talk about dark matter, they're describing something with very specific properties. It has mass. That much is clear, because it pulls on things with gravity. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. That's why we call it dark. And most importantly, it doesn't seem to interact with ordinary matter very much at all, except through gravity. Imagine a ghost walking through a wall. The ghost doesn't bounce off, doesn't knock anything over, just passes through as if the wall weren't there. Dark matter is a bit like that. It passes through planets, through stars, through you and me, barely noticing we exist. Right now, as you lie here listening, dark matter particles might be streaming through your body. Trillions of them. And you don't feel a thing. That sounds eerie, perhaps. But it's also kind of peaceful. The universe is full of these gentle, invisible currents. And they've been flowing for billions of years, undisturbed, holding everything together. So what could dark matter be made of? Scientists have proposed many candidates. Let's talk about a few of them. One of the most popular ideas involves particles called WIMPs. That stands for Weakly Interacting Massive Particles. The name tells you almost everything. These would be particles with mass, but they interact only weakly with ordinary matter. WIMPs would be left over from the early universe. Moments after the Big Bang, the leading theory for how our universe started. When everything was hot and dense, all kinds of particles were created. Most of them decayed or annihilated, but some, the stable ones, survived. WIMPs, if they exist, would be those survivors, scattered throughout space, invisible, silent, but massive enough, collectively, to shape the structure of galaxies. Scientists have built detectors deep underground to search for WIMPs. These detectors are shielded from cosmic rays and other interference. They wait patiently for a dark matter particle to collide with an atom. Just once would be enough. One collision would prove they exist. But so far nothing. The detectors have been running for years. And the WIMPs, if they're out there, haven't made themselves known. That doesn't mean they don't exist. It might just mean they interact even more weakly than we thought, or that we're looking in the wrong way. Another idea involves particles called axions. These would be much lighter than WIMPs. Tiny, almost massless, but incredibly numerous. Trillions upon trillions of them in every cubic centimeter of space. Axions were originally proposed to solve a different problem in physics. But scientists realized they could also be dark matter. And because they're so light, they'd behave almost like a wave, a ripple in space itself. Some experiments are now searching for axions using powerful magnetic fields. The idea is that an axion, passing through the field, might convert into a photon, a particle of light, and that photon could be detected. Again, so far, no definitive detection. But the search continues. There are other candidates too. Sterile neutrinos, primordial black holes, exotic particles we haven't even imagined yet. Each idea has its strengths. Each has its challenges. And each reminds us how much we still have to learn. But here's something important to remember. Even though we don't know what dark matter is, we know it's there. The evidence is overwhelming. Galaxies wouldn't hold together without it. Clusters wouldn't form. The cosmic microwave background, that faint glow left over from the Big Bang, wouldn't have the patterns we observe. Dark matter is woven into the fabric of the universe. It's part of the structure, part of the story, and that structure is beautiful. Computer simulations show how dark matter shaped the cosmos. In the early universe, dark matter clumped together under its own gravity. It formed a kind of scaffolding, a web of invisible filaments stretching across space. Ordinary matter, the stuff we can see, fell into this scaffolding. It pooled in the densest regions, and there it formed stars, and galaxies, and eventually planets, and us. Without dark matter, none of this would exist. The universe would be smooth and empty. No stars, no light, no life. So, in a way, we owe our existence to this mystery, to these invisible particles, whatever they are, that gathered in the early cosmos and gave structure to everything that came after. Think about that for a moment. Something you can't see, can't touch, can't detect directly, made your existence possible. It's humbling and oddly comforting, because it means we're part of something bigger, something that reaches back to the beginning of time, something that connects us to the farthest galaxies and the deepest mysteries. Dark matter doesn't threaten us. It doesn't disturb us. It just quietly does its job, holding the universe together, allowing stars to shine and planets to form and life to emerge. And now, as you rest, you can take comfort in that, in the idea that the universe, for all its mysteries, has a kind of order, the kind of balance, the dark and the light, the seen and the unseen, both necessary, both beautiful. So let go of any need to understand it all. Let go of any frustration or confusion. The universe doesn't ask us to understand everything. It just invites us to wonder. And wondering in the quiet of the night is one of the most peaceful things we can do. Part 4. When gravity itself might be different. Now let's consider another possibility. A different kind of idea. One that asks, what if there is no dark matter at all? What if, instead, gravity itself works differently to what we think? This idea might sound radical, and in some ways it is, but it's also a perfectly reasonable scientific question, and exploring it can help us understand why science is a conversation, not a proclamation. The laws of gravity we use today come mostly from Albert Einstein. His theory of general relativity, published in 1915, describes gravity as the bending of space and time. Mass tells space how to curve, and that curvature tells matter how to move. Einstein's theory has been tested countless times. It predicted the bending of light around the sun, the precession of Mercury's orbit, the existence of black holes, gravitational waves, and every test has confirmed it. General relativity works beautifully. But here's the thing. All those tests were done in our solar system, or with nearby stars, or with colliding black holes. Relatively small scales, cosmically speaking. What if gravity behaves differently on the scale of galaxies, or clusters of galaxies? What if the equations we use break down when distances become truly vast? This is the core of an idea called modified gravity, and it comes in several forms. One of the earliest and most famous is called MOND. That stands for Modified Newtonian Dynamics. It was proposed by a physicist named Mordechai Milgram in the early 1980s. Milgram noticed something interesting. The rotation curves of galaxies, the ones that suggested dark matter, all showed a similar pattern. The deviation from expected behavior happened at a specific threshold, when the gravitational acceleration became very, very weak. He wondered, what if Newton's laws of motion don't quite work when accelerations are extremely small? What if, in those conditions, gravity becomes a bit stronger than expected? If you modify the equations just slightly, in just the right way, you can explain the rotation curves without needing dark matter at all. It's an elegant idea. Instead of adding invisible matter, you change the rules. Just a little. Just enough. And for a while, MOND worked surprisingly well. It predicted the rotation curves of many galaxies accurately. It explained patterns that dark matter models struggled with. But MOND has problems too. It doesn't explain galaxy clusters as well. It struggles with gravitational lensing, the way light bends around massive objects. And it doesn't fit neatly into our broader understanding of physics. Still, the idea persists, because it asks an important question. A question science should always ask. Are we sure our fundamental theories are right? There are more sophisticated versions of modified gravity too. Theories that tweak Einstein's equations rather than Newton's. Theories with names like Tevis and Ackwell and These theories attempt to do what MOND does, but in a way that's consistent with relativity. They modify the structure of space-time itself. Space-time is the interconnectedness of space and time, affecting time's passage and gravity. They add new fields or new dimensions or new rules about how gravity propagates. Some of these theories can explain galaxy rotation curves and cluster dynamics, and even some features of the cosmic microwave background. Not perfectly, but well enough to keep scientists interested. And here's what's fascinating. Science doesn't require us to choose one side and defend it forever. Scientists are allowed to explore multiple ideas at once, to test them, to see which one fits the data better. Dark matter and modified gravity are both on the table, both being investigated, both taken seriously, because the goal isn't to win an argument. It is to understand the universe. And sometimes the path to understanding is indirect. In recent years, new observations have added interesting wrinkles to the debate. Some measurements of galaxy rotation curves fit modified gravity models better than expected. Other observations, like the way galaxies cluster on very large scales, still favor dark matter strongly. There's a phenomenon called the bullet cluster, two galaxy clusters that collided and passed through each other. When astronomers mapped where the mass was using gravitational lensing, they found something striking. The visible matter, mostly hot gas, was in one place, but most of the mass detected through lensing was somewhere else, separated, as if the invisible matter passed right through the collision while the visible matter got stuck. This is hard to explain with modified gravity, but it's exactly what dark matter theory predicts. And yet, modified gravity proponents have responses. They argue that the situations are more complex, that the theories can be adjusted, that more data is needed. This back and forth is healthy. It's how science works. Hypothesis, observation, revision, debate. No one knows for certain yet. And that uncertainty, that open question, is part of the beauty, because it means the universe still has secrets. It means we're still learning, still refining our understanding, still looking up at the sky and asking, how does this really work? So, as you lie here now, you don't need to pick a side. You don't need to decide whether dark matter is real or whether gravity needs modifying. You can simply appreciate that both ideas exist. That smart, dedicated people are working on both. That the truth, whatever it is, will eventually emerge from careful observation and honest inquiry. The universe isn't in a hurry. It's been here for 14 billion years. It can wait while we figure things out. And you, right now, can rest in that patience. In the slow, steady progress of science. In the knowledge that mysteries don't need to be solved now. They can wait until tomorrow, or next year, or the next century. The stars will still be there. The galaxies will still be spinning. And the questions will still be worth asking. Part 5. The whispers that change the conversation. Let's talk about the indications of scientific research on the subject of dark matter in recent years, as well as some that provided much food for thought as recently the last few days and weeks leading up to the creation of this video. New measurements, new data, new reasons for scientists to pause and reconsider. You may have seen the headlines of articles claiming that our universe could come to an end with the Big Crunch, and that Einstein's theory of relativity might be wrong. That everything we thought we knew about the cosmos is being questioned. These headlines can sound alarming, dramatic, like the foundations of physics are crumbling. But the reality is nowhere near so harsh, more nuanced. And understanding what actually happened can be deeply calming. because it shows us how science really works. In 2024 and into 2025, several research teams published observations of galaxies in the early universe. These galaxies were very far away, so far that their light has taken billions of years to reach us. We're seeing them as they were long, long ago. What astronomers found was surprising. These early galaxies seemed more massive than expected, more organized, more mature. According to models that include dark matter and dark energy, galaxies should have taken longer to form. The early universe should have been messier, more chaotic. Stars and galaxies should have been smaller, less structured. But these observations suggested otherwise. The galaxies looked too big, too old, too well-formed for their age. This created a puzzle. If the models are right, where did these massive galaxies come from so quickly? How did they assemble so fast? Some scientists began to wonder, could our models be wrong? Could dark matter work differently to the way we thought? Could gravity itself behave in unexpected ways in the early universe? Around the same time, other studies looked at how galaxies rotate in different environments. Some found rotation patterns that fit better with modified gravity theories than with standard dark matter models. Not all galaxies, not all the time, but enough to make people pay attention. These weren't lone cranks or fringe voices. These were careful observations published in respected journals. Data that needed to be taken seriously. And so the conversation shifted. Just a little. Just enough. Scientists started asking, what if we've been missing something? What if the picture is more complicated than we realized? But here's the important part. None of this means dark matter is wrong. None of it means Einstein was mistaken. What it means is that the universe is showing us something subtle, something we didn't predict, and we need to figure out what that something is. Maybe the models of how galaxies form need adjusting. Maybe there are processes in the early universe we don't fully understand yet. Star formation, gas dynamics, the way matter clumps together. Maybe dark matter particles interact with each other in ways we haven't accounted for. Maybe they have properties we haven't discovered. Or maybe, just maybe, gravity does something unusual under extreme conditions. In the intense environments of the early universe, or in the sparse regions between galaxies. All of these are possibilities, and scientists are exploring all of them. This is what it looks like when science encounters something unexpected. It doesn't panic. It doesn't abandon everything. It pauses. It looks closer. It asks better questions. There's a phrase scientists use: extraordinary claims require extraordinary evidence. It means that before you overturn a well-established theory, you need overwhelming proof. Not just one odd measurement, but many, from multiple sources, all pointing in the same direction. Right now we have intriguing hints, interesting data, reasons to investigate further, but we don't yet have extraordinary evidence. We don't have a complete alternative theory that explains everything better than the current one. And that's okay. That's how it should be. Science is patient. It waits for replication, for independent confirmation, for competing explanations to be tested and compared. Sometimes new observations turn out to be errors. Instruments miscalibrated. Data misinterpreted. It happens, not because scientists are careless, but because the universe is hard to measure. Space is vast. Light is faint. Noise is everywhere. Other times new observations are real, but their explanation is simpler than it first appeared. A known process, just happening in an unexpected way. And occasionally, very occasionally, new observations point to something genuinely revolutionary. A new particle, a new force, a new understanding of nature. We don't know yet which category these recent findings fall into. And that's the exciting part. The mystery isn't solved. The question is still open. But let's be clear about what hasn't changed. The evidence for dark matter from galaxy rotation curves is still strong. The evidence from gravitational lensing is still strong. The evidence from the cosmic microwave background is still strong. The evidence for the expansion of the universe, driven by dark energy, is still strong. Einstein's general relativity still passes every test we throw at it. In our solar system, around black holes, in gravitational wave detections. What we're seeing now isn't the collapse of a theory. It's the refinement of one, the addition of new details, the exploration of edge cases. Think of it like this. Imagine you have a map of a forest. It shows the trails, the rivers, the major landmarks. You've used this map many times. It's reliable. Then one day you discover a small pond that isn't on the map. Does that mean the whole map is wrong? That you should throw it away? It means the map is incomplete. It means you need to add the pond. Maybe explore that area more carefully. Maybe discover why the pond wasn't noticed before. The map is still useful, still mostly accurate. It just needs updating. That's where cosmology is right now. We have a good map, a reliable framework. Dark matter, dark energy, general relativity. These ideas explain an enormous amount, but the universe is handing us a few details that don't quite fit, a pond that's not on the map. And so we explore, we measure, we think. This is the human side of science, the part that's often hidden behind equations and jargon, the part that involves doubt, debate, curiosity, humility. Scientists are not gods pronouncing truth from on high. They're explorers, mapmakers, piecing together a picture of reality one observation at a time. And when something doesn't fit, they don't ignore it. They lean in, they investigate, they wonder. So if you've been worried by those headlines, you can rest easy. The universe isn't broken. Our understanding isn't collapsing. We're just learning, growing, getting closer to the truth. And that truth, whatever it turns out to be, will be beautiful. Because the universe always is. So let that thought settle. Let it ease any tension, any worry. The cosmos is still here, still vast, still full of wonders, and we're still figuring it out. Slowly, carefully, together. Part 6, the force that stretches everything. Now let's turn our attention to something even stranger than dark matter. Something called dark energy that we have already mentioned here. If dark matter is invisible glue holding galaxies together, dark energy is the opposite. It's an invisible pressure pushing everything apart. And it dominates the universe. To understand dark energy, we need to talk about expansion, about how the universe is growing, and how, against all expectation, that growth is speeding up. In the 1920s, astronomers discovered that the universe isn't static. It's expanding. Every galaxy is moving away from every other galaxy. Not because they're traveling through space, but because space itself is stretching. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, not because they're walking across the rubber, but because the rubber is expanding. That's what's happening to the universe. Space itself is growing, and galaxies are carried along with it. For decades, scientists assumed this expansion was slowing down. After all, gravity pulls everything together. So the expansion, set in motion by the Big Bang, should gradually lose momentum, like a ball thrown into the air, accelerating upward more slowly until it eventually falls back. But in 1998, two teams of astronomers made a discovery that shocked everyone. They were studying distant supernovae, exploding stars so bright they can be seen across billions of light years. These supernovae serve as cosmic mile markers. Their brightness tells us how far away they are. And by measuring how fast they're moving away from us, we can tell how the universe has expanded over time. What the astronomers found was astonishing. The distant supernovae were dimmer than expected, farther away than they should be. This could only mean one thing. The expansion of the universe isn't slowing down. It's speeding up. Something is pushing space apart. Something with enough power to overcome gravity, to accelerate every galaxy away from every other. They called this something dark energy, and the discovery earned a Nobel Prize. But what is dark energy? Honestly, we have even less idea about the answer to that question than we do about dark matter. It's one of the deepest mysteries in all of physics. The simplest explanation is that dark energy is a property of space itself, a kind of energy that's woven into the fabric of the vacuum. Everywhere. Boys. Einstein actually predicted something like this. He called it the cosmological constant, a term in his equations that represented a kind of pressure inherent to empty space. At first, Einstein thought this was a mistake. He added it to make the universe static because he didn't know the universe was expanding. When expansion was discovered, he called the cosmological constant his greatest blunder. But it turns out he might have been right all along, just for different reasons. If empty space has energy, and if that energy has a kind of negative pressure, it would push space apart. And the more space there is, the more dark energy there is. So as the universe expands, the amount of dark energy increases, and the expansion accelerates. It's a runaway process. Expansion creates more space. More space means more dark energy. More dark energy means faster expansion. And this process will never stop. Trillions of years from now, the universe will be much larger than it is today. Galaxies will be so far apart that light from one will never reach another. The sky will grow dark. Stars will burn out. And the universe will become cold and empty. But don't scramble to get your affairs in order just yet. This won't happen for an unimaginably long time. Our sun has billions of years left. Our galaxy will continue to thrive. Life, if it endures, will have eons to explore and grow. The end is so far away it might as well be forever. And in the meantime, dark energy is actually quite gentle. It only affects the largest scales. Between galaxy clusters, across cosmic voids. It doesn't pull your body apart. It doesn't tear galaxies to shreds. On the scale of planets, stars, even whole galaxies, gravity is much stronger. Dark energy is only noticeable when you look at truly immense distances. So you can rest easy. Dark energy isn't a threat. It's just a feature of the cosmos. A slow, steady pressure that shapes the universe on its grandest scales. But why does space have this energy? Where does it come from? No one knows. Quantum mechanics suggests that empty space should have energy. But when physicists calculate how much, they get a number that's absurdly large. Enormously bigger than what we observe. This discrepancy is called the cosmological constant problem, and it's one of the biggest unsolved puzzles in physics. Some scientists think dark energy might not be constant. Maybe it changes over time. Maybe it's not a property of space itself, but a new kind of field. Something dynamic, evolving. Others wonder if dark energy is a sign that general relativity breaks down on cosmic scales. That we need a new theory of gravity that naturally includes this accelerated expansion. These are open questions, active areas of research, and the answers, when they come, will deepen our understanding of reality in profound ways. But for now we live in a universe shaped by dark energy. A universe that's expanding, growing, stretching. And there's something oddly comforting about that. The universe isn't shrinking inward, collapsing, ending. It's opening outward, making room, creating space for new possibilities. It's as if the cosmos itself is taking a deep breath, slow, endless, expanding into the infinite. And you, right now, are part of that, part of a universe that's growing, changing, unfolding. So breathe with it. Let your chest rise and fall. Let your body relax into the moment. The universe is expanding, and you are here to feel at peace. Part 7. Seeing the invisible through shadows and light. Now let's explore something wonderful. How do astronomers study things they cannot see? How do they measure dark matter when it doesn't emit light? How do they map dark energy when it has no color, no brightness, no substance? The answer is beautiful in its cleverness. Scientists look for the effects these invisible things have on what we can see. They watch shadows. They measure distortions. They study patterns. It's like being a detective who never sees the criminal, but finds fingerprints everywhere. One of the most powerful tools is called gravitational lensing. It's based on a prediction from Einstein's general relativity. Mass bends space. And when space bends, light traveling through it bends too. Imagine a glass lens. Light passing through curves toward the thickest part. The lens focuses light, magnifies images, changes what we see. Gravity does the same thing. A galaxy or a cluster of galaxies acts like a lens. Light from objects behind it gets bent as it passes through the curved space around the cluster. This means we can see distant galaxies that would otherwise be too far away. They appear stretched, distorted. Sometimes multiple images of the same galaxy appear, like reflections in a funhouse mirror. By measuring these distortions, astronomers can map where the mass is, or the mass, both visible and invisible. And what they find is striking. The lensing is far stronger than the visible matter alone could produce. There's much more mass present than we can see in stars and gas. This is one of the strongest pieces of evidence for dark matter. The lensing doesn't care what kind of matter is there. It just responds to mass. And there's clearly much more mass than meets the eye. Scientists have created maps of dark matter this way. Beautiful, ghostly maps showing how invisible matter is distributed across the universe. It forms a web, filaments and nodes. Galaxies sit in the densest regions, like cities along highways. These maps show us the skeleton of the cosmos, the hidden architecture, the framework upon which everything visible is built. Another tool is the cosmic microwave background. This is light from the early universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Light that had been scattered by free electrons could finally travel freely. That light has been traveling ever since, stretched by the expansion of space, cooled from visible light to microwaves. Today we can detect it. It fills the entire sky. A faint glow, just a few degrees above absolute zero. And it's not perfectly smooth. It has tiny variations, hot spots and cold spots, temperature differences of just a few millionths of a degree. These variations are incredibly important. They're the seeds of structure. Regions that were slightly denser became the places where galaxies would eventually form. Regions that were slightly less dense became the voids between them. By studying the pattern of these variations, scientists can learn about the composition of the universe. How much ordinary matter? How much dark matter? How much dark energy? The cosmic microwave background is like a baby picture of the universe. And from that picture we can extrapolate everything that came after. The growth of structure, the formation of galaxies, the acceleration of expansion. The data fits the model remarkably well. A universe with about 5% ordinary matter, 27% dark matter, and 68% dark energy. These numbers aren't guesses. They're measurements. Precise, consistent across multiple methods. Another technique involves watching how galaxies cluster. Galaxies aren't scattered randomly across space. They clump together. They form groups, clusters, superclusters, filaments stretching across hundreds of millions of light years. This clustering is shaped by gravity, by how matter, both visible and dark, pulls on itself over cosmic time. Scientists use telescopes to map millions of galaxies, to measure their positions, their distances, their motion, and from this enormous data set, they can infer how much dark matter there is, how it's distributed, how it's affected by dark energy. There are surveys with names like SDSS and DESI and Euclid. They're mapping the universe in exquisite detail, creating three-dimensional atlases of cosmic structure. Each galaxy is a data point. Each cluster is a measurement. And together they paint a picture of a universe shaped by invisible forces. Then there's the motion of galaxies themselves. We talked earlier about rotation curves, how stars and galaxies move too fast. But there's more. Galaxies in clusters orbit around the cluster's center. That motion depends on the total mass of the cluster. By measuring how fast galaxies are moving, astronomers can weigh the cluster. And once again, the mass is far greater than the visible matter suggests. All these methods, gravitational lensing, the cosmic microwave background, galaxy clustering, galaxy motion, they all point to the same conclusion. Dark matter is real. Dark energy is real. The universe is full of things we cannot see directly, but we can see their effects, their fingerprints, their signatures written in the patterns of light and structure. It's a bit like listening to music. You can't see sound waves, but you can hear the melody, feel the rhythm, understand the song. Astronomers are listening to the universe, watching how light dances, how galaxies move, how space itself responds to the mass and energy within it. And from all these observations, a coherent picture emerges. Not perfect, not complete, but clear enough to guide our understanding. The universe is not hiding its secrets out of spite. It's revealing them slowly, one measurement at a time, one pattern at a time. And there's something deeply satisfying about that. The universe follows rules. It leaves clues. And with patience, with careful observation, we can piece those clues together. So, as you relax, think about those maps of dark matter. Those images of the cosmic microwave background. Those surveys of millions of galaxies. Think about the dedication required to gather that data. The teamwork, the years of patient observation. And think about what it reveals. A universe far stranger and richer than our eyes alone could ever show us. The invisible made visible, not by seeing it directly, but by watching how it shapes everything around it. Like wind in the trees. You can't see the wind, but you can see the branches sway, the leaves flutter, and from that you know the wind is real. Dark matter and dark energy are like that wind. Invisible, but undeniably there. Part 8. Einstein's universe and where the cracks appear. Let's talk about Albert Einstein, about his theory, about why it matters so much to this story. General relativity is more than 100 years old now, published in 1915, and yet it remains the foundation of modern cosmology. It's a theory about gravity, but it's also about space. The structure of reality itself. Einstein realized something profound. Gravity isn't a force that reaches across empty space and pulls on things. Gravity is the shape of space itself. Mass tells space how to curve, and curved space tells matter how to move. Imagine a trampoline. Place a bowling ball in the center. The fabric dips, creates a well. Now roll a marble across. It doesn't travel in a straight line. It curves toward the bowling ball. Not because the ball is pulling it, but because the surface itself is curved. That's gravity in Einstein's view. Planets orbit stars because the star curves space around it. Light bends near massive objects because it's following the curves in spacetime. This theory has been tested over and over, and every test confirms it. When light from a distant star passes near the sun during a solar eclipse, it bends. Just as Einstein predicted. The first observation of this, in 1919, made Einstein famous. The orbit of Mercury, the closest planet to the sun, has a slight wobble. Newton's theory couldn't explain it, but Einstein's could. Perfectly. Gravitational waves, ripples in spacetime caused by colliding black holes, were predicted by Einstein in 1916. They were detected for the first time in 2015, nearly a century later, and they matched the predictions exactly. Black holes, those regions of space where gravity is so strong that nothing can escape, are a natural consequence of general relativity. And we've now observed them directly, taken pictures of their shadows, watched stars orbit around them. General relativity works. It works extraordinarily well. And yet, there are places where it seems incomplete. Places where tensions appear. One of those places is dark matter. General relativity predicts how galaxies should move based on the visible matter. And they don't move that way. So either there's invisible matter or the theory needs modifying. Most scientists favor the dark matter explanation because it's simpler. It doesn't require changing a theory that works so well everywhere else. But, as we discussed earlier, some scientists explore the alternative: modified gravity, changing Einstein's equations slightly to account for the anomalies. This isn't heresy. It's good science. Every theory has limits. Newton's theory worked beautifully for centuries. Until it didn't. Until Mercury's orbit didn't quite fit. Until light bending was observed. Then Einstein came along with a better theory. One that included Newton's as a special case, but extended further. Maybe someday, someone will find a theory that includes Einstein's as a special case, but extends even further. Or maybe not. Maybe general relativity is correct, and we just need to find the dark matter particles. Only time and observation will tell. Another place where cracks appear is with dark energy. Einstein's equations allow for a cosmological constant, a term that represents energy in empty space. And that's how most scientists interpret dark energy. But there's a problem. The value of this constant is incredibly small. Far, far smaller than quantum mechanics suggests it should be. Why is it so small? Why does it have the precise value it has? No one knows. And that's troubling. Because in physics, when numbers need to be fine-tuned to incredible precision, it often means we're missing something. Some deeper principle. Some underlying reason. Some scientists think dark energy isn't constant at all. That it changes over time. That it's a field like the magnetic field or the electric field, but something new. If that's true, general relativity might need modification. Or supplementation, some additional piece to explain this evolving field. Then there's the problem of quantum mechanics. Einstein's theory describes gravity on large scales. Planets, stars, galaxies, black holes. It works beautifully there. But at very small scales, quantum mechanics takes over. And these two theories, general relativity and quantum mechanics, don't fit together. They use different mathematics, different principles, different assumptions about how reality works. Physicists have tried for decades to unify them, to create a theory of quantum gravity, something that works at all scales, from the smallest particles to the largest structures in the universe. But so far, no success. Not definitively. String theory, loop quantum gravity, other approaches, all promising, all incomplete. This isn't a failure. It's the frontier, the edge of human knowledge, the place where the next great discovery might happen. And when it does, it might shed light on dark matter and dark energy too. Because these mysteries might all be connected. Different symptoms of the same underlying gap in our understanding. But here's what's important to remember. These cracks, these tensions, these unsolved problems, they don't mean Einstein was wrong. They mean Einstein's theory is incomplete, which is very different. Newton wasn't wrong about gravity. His laws still work perfectly for most everyday situations. We use them to launch satellites, to calculate orbits. They're just not the whole story. Einstein isn't wrong either. His theory is our best description of gravity. It makes predictions that are confirmed again and again. But like all scientific theories, it has limits. Places where it doesn't quite fit. Questions it can't quite answer. And that's okay. That's beautiful even. because it means there's more to discover, more to understand. The universe is still teaching us, still showing us that reality is deeper, stranger, more subtle than we imagined. Science isn't about final answers. It's about better and better approximations, closer and closer approaches to truth. Each generation builds on the last, adds new observations, new theories, new understanding, and the picture gets clearer, more complete, more accurate. So when you hear that Einstein's theory might need modification, don't think of it as a crisis. Think of it as an opportunity to learn something new, to expand our knowledge, to see the universe with fresh eyes. Einstein would have loved that. He was curious, playful, always questioning, always wondering. He didn't hand down laws from on high. He explored, he imagined, he followed the mathematics wherever it led. And sometimes it led to places he didn't expect, to an expanding universe, to black holes, to gravitational waves. The next Einstein, whoever they are, will do the same. They'll take what we know and push it further, into new realms, new scales, new phenomena, and the universe will reveal more of itself. Slowly, patiently, as it always has, as it always will. So rest easy. The universe isn't falling apart. Our understanding isn't crumbling. We're just at the edge of the map, where the known meets the unknown. And that's the most exciting place to be. Part 9. The patient work of science. Let's slow down now, take a breath, and talk about something important, something that doesn't always make it into the headlines. The process of science, how it actually works, why it takes time, why scientists don't immediately overturn theories when something unexpected appears. There's wisdom in this slowness, a kind of careful patience that serves us well. When a team of scientists makes a new observation, something that challenges existing ideas, the first response isn't celebration. It's caution. They ask themselves questions. Could this be an error? Is the instrument calibrated correctly? Did we account for all sources of noise? Is there another explanation we haven't considered? Science is rigorous because it has to be. The universe is complicated, easy to misinterpret, easy to see patterns that aren't really there. So scientists check, and double check, and check again. They share their data with colleagues. They describe their methods in detail. They publish papers that anyone can read and critique. And then other scientists try to replicate the result, using different instruments, different methods, different samples of data. If the observation holds up, if multiple teams find the same thing, then confidence grows. The result is probably real, probably meaningful. But even then, even when an observation is confirmed, it doesn't immediately overturn existing theories. First, scientists try to explain the observation within the existing framework. Maybe there's a known process we didn't account for. Maybe the theory predicts this, but we didn't realize it until now. Only when all those attempts fail, when the observations simply cannot be reconciled with the current theory, do scientists seriously consider alternatives. And even then, the new theory has to do more than explain the new observation. It has to explain everything the old theory explained, plus the new data. It has to be more comprehensive, more accurate. This is a high bar. And it should be, because the existing theory, whatever it is, didn't come from nowhere. It's the result of decades, sometimes centuries, of work. Thousands of observations, countless tests. To replace it requires overwhelming evidence. Not just one anomaly, but many, all pointing clearly in a new direction. This is why dark matter hasn't been displaced by modified gravity. Even though modified gravity can explain some observations, dark matter explains more, and explains them more completely. This is why Einstein's general relativity is still our working theory of gravity. Even though there are tensions, even though there are mysteries, it works too well in too many situations to abandon. But here's the beautiful part. Scientists aren't closed-minded. They're not stubbornly clinging to old ideas. They're just careful, methodical, patient. They're willing to be proven wrong. In fact, many scientists would be thrilled to discover something revolutionary. That's what earns Nobel Prizes. That's what makes careers. But they want to be sure. They want the evidence to be solid, the reasoning to be sound, because the cost of being wrong is high. If you claim a major discovery and it turns out to be an error, you lose credibility. You waste resources. You send the field down a dead end. So scientists move carefully. They follow the evidence. They test ideas rigorously, and they accept that this takes time. Let's think about the recent observations we discussed earlier. The galaxies in the early universe that seemed too massive. The rotation curves that fit modified gravity better than expected. These are intriguing, worth investigating, worth taking seriously, but they're not yet conclusive, not yet overwhelming. Maybe those early galaxies formed through processes we don't fully understand yet. Maybe there were bursts of star formation we didn't account for. Maybe our models of galaxy evolution need refinement, but not replacement. Maybe those rotation curves have measurement uncertainties we haven't fully characterized. Maybe there are environmental factors that affect how galaxies spin. These aren't excuses. They're legitimate questions. Questions that need answers before we can draw firm conclusions. And answering them takes time. More observations. More analysis. More careful thought. In the meantime, scientists do what they always do. They keep working. They refine their models. They build better instruments. They gather more data. There's something deeply comforting about this approach. It means science isn't driven by fashion or hype. It's driven by evidence, by careful reasoning, by a collective commitment to getting things right. Individual scientists can be wrong, often are wrong. That's part of the process. But the community as a whole, through this system of checks and balances, of replication and peer review, gradually converges on truth. Not perfectly, not quickly, but reliably. Think about how many scientific ideas from the past have stood the test of time. Atoms, evolution, plate tectonics, the germ theory of disease, relativity, quantum mechanics. These weren't accepted overnight. Each faced skepticism. Each required extensive evidence. But once that evidence accumulated, once the ideas proved their worth, they became foundational, bedrock, part of our reliable understanding of reality. Dark matter and dark energy are on that path. Not yet as certain as atoms or evolution, but supported by enough evidence that most scientists consider them real. Could that change? Of course. That's the nature of science. Every idea is provisional. subject to revision if better evidence comes along. But the bar is high, and it should be, because we're not just playing intellectual games. We're trying to understand the universe as it actually is, not as we wish it to be, not as it would be convenient for it to be, as it actually is. And the universe doesn't care about our preferences. It doesn't adjust itself to fit our theories. It just is what it is. Our job is to observe carefully, think clearly, and follow the evidence wherever it leads. Even if it leads somewhere unexpected, even if it means revising cherished ideas. Science is humble in that way. It's willing to admit error, to change course when needed, but it's also careful, cautious, patient, because getting things right matters more than getting them quickly. So when you hear about new observations that challenge existing theories, don't worry. Don't think the foundation is crumbling. Think of it as science doing what science does. Exploring, questioning, testing. The process is working exactly as it should, and in time the truth will emerge. Slowly, carefully, but surely. Vera Rubin, whom we talked about earlier, spent decades measuring galaxy rotation curves. Night after night at the telescope, image after image, calculation after calculation. She knew she was onto something important, but she also knew it would take time for the scientific community to accept it, time for the evidence to accumulate, time for the implications to sink in. She never won the Nobel Prize, though many believe she should have. She died in 2016, before dark matter was fully confirmed. But her work lives on. It shaped an entire field, inspired countless other scientists, changed how we understand the cosmos. That's dedication. That's passion. That's love for the work itself, regardless of recognition. The universe is patient. It's been here for billions of years. It can wait while we figure things out. And we, in turn, can rest in that patience, in the knowledge that the work is being done. The questions are being asked. The observations are being made. One measurement at a time. One paper at a time. One careful step at a time. Toward deeper understanding. Toward clearer truth. Part 10. What comes next in the search? Let's scan ahead now, toward what might come next. What scientists are planning. What observations might help us understand. The search for dark matter and dark energy continues, and it's entering an exciting phase. New telescopes, new experiments, new ways of seeing. In space, there are missions being planned. Satellites that will map the universe with unprecedented precision. The Euclid telescope, launched recently, is surveying billions of galaxies, measuring their shapes, their distances, their positions. From this enormous data set, scientists can map dark matter across the cosmos, see how it clusters, how it evolved over time. They can also measure how dark energy has affected the expansion of the universe, whether it's truly constant or whether it changes. The James Webb Space Telescope is looking deeper into space than ever before, seeing galaxies from the very early universe. Those puzzling massive galaxies we mentioned, Webb is studying them, taking detailed measurements, trying to understand how they formed so quickly. Maybe there's an explanation within our current models. Maybe we'll discover something new. Either way, we'll learn. On the ground, there are enormous telescopes being built. Telescopes with mirrors tens of meters across. They'll be able to see fainter objects, Measure light more precisely. Study the details of distant galaxies and stars. And there are experiments deep underground, in mines, in tunnels, shielded from cosmic rays. These detectors wait for dark matter particles to collide with atoms. Just one collision would be enough. One clear signal. Different experiments use different approaches, different materials, different detection methods. Some use tanks of liquid xenon. Others use crystals of germanium or silicon. Others use different techniques entirely. Cast a wide net. Try everything. Because we don't know exactly what we're looking for. Maybe dark matter interacts in ways we haven't anticipated. Maybe we need a new kind of detector, a new approach. Scientists are creative. They're trying novel ideas, looking in unexpected places. There are experiments searching for axions using powerful magnets. Experiments looking for primordial black holes. Experiments testing whether dark matter might interact with itself. And there are theoretical physicists working on new models, new ideas about what dark matter and dark energy might be. Some are exploring connections to quantum mechanics, to string theory, to ideas about extra dimensions. Others are developing more sophisticated versions of modified gravity, testing whether they can explain all the observations. The conversation is rich. The possibilities are many. And here's what's important. We will figure this out. Eventually. Maybe not this year. Maybe not this decade. But eventually. Because we're asking the right questions. We're making the right observations. We're building the right tools. And the universe, for all its mysteries, follows consistent laws. It's comprehensible. Part 11. A final thought before sleep. And now we come to the end. The final moments of our journey through the dark. We've traveled far. Through galaxies and clusters. Through invisible matter and mysterious energy. Through the patient work of science and the wonder of not knowing. And what have we learned? What can we take with us through to our next awakening? Perhaps this, that the universe is vast beyond imagination, ancient beyond comprehension, and mostly invisible, that everything we can see, all the stars and planets and light, is just a tiny fraction of what exists. The rest is dark, hidden, known only by its effects. And somehow that's comforting, because it means reality is deeper than appearances. There's more going on than meets the eye. The surface is not the whole story. In our own lives, we sense this too, that there's more beneath the surface. Hidden depths, invisible connections. The universe confirms it, shows us that the hidden can be real, that the invisible can be powerful. Dark matter holds galaxies together. Dark energy pushes the cosmos apart. Both invisible, both essential. Without them, none of this would exist. Not the stars, not the planets, not us. We owe our existence to mysteries, to things we don't fully understand. And that's okay. More than okay. It's beautiful, because it means we're part of something larger than ourselves. Something that stretches back to the beginning of time. Something that will continue long after we're gone. We're temporary. A moment in cosmic time. But we're also real. We're part of the story. Part of the structure. Made of atoms forged in stars. Held together by forces that govern galaxies. Thinking thoughts that reach across billions of light years. Conscious matter. the universe aware of itself, pondering its own nature. That's what we all are, right now. Just pieces of the cosmos, wondering about the cosmos, connected to it all, and the dark matter flowing through you. The dark energy stretching space around you. They're part of your story, not separate, not distant, but here, woven into the fabric of reality that includes you. You're safe in this universe, held by gravity, surrounded by space, part of the pattern. And as you drift towards sleep, the questions that linger don't need answers now. The mysteries don't need solving. The universe will still be here to study whenever we are ready. Dark matter will still be holding galaxies together. Dark energy will still be stretching space apart. Scientists will still be searching, observing, thinking, and the cosmos will continue its slow expansion, its patient unfolding, its eternal evolution. All of this will continue. Without your attention, without your concern, you can rest, you can sleep, you can let it all be.